Hi, my name's Matt Denton, this is Mantis Hacks, and this is part 2 of my Dio Droid build. This build is based on Michael Baddeley's 3D printed Dio design. I'm making tweaks and modifications of my own as I go along. I've left plenty of information in the description section below, and of course don't forget to subscribe. In this video I'm going to tackle the electronic stack which goes on top of here, and maybe start to look at the head design. So anyway, let's start by having a look at what I've done with the electronic stack in the CAD. So what I've been working on mostly is the deck itself. I've added all sorts of cable tie points along the sides just because I don't know my cable routing yet. I've also added this switch over here. This is a 6 amp toggle switch. I've added these little gear protectors inside. There you go, you can see that they cover the gears up so cables running through the middle there won't get pulled into them. This is a Lynmotion power block, and it's basically 4 Molex connectors connected up in parallel. I don't really like these jack plugs, so I'm actually going to feed power directly from the batteries into the board, obviously via the switch. What I'm going to do is take one of them and supply power into the motor driver board, and the serial information will go up to the Arduino. 2 of them at the back here will probably drive the LSS servos, which are down here. Final socket will go back down through the electronic stack here, and then down the axle, up the neck and into the head. I've made these little stands up here for the motor board to fit onto. On top of that we've got our Arduino, which is the MKR W1010 I think. This was an SD card carrier, but I'm actually going to replace it just with a standard proto board, and that's so I can wire in like the serial data and plug in things like the Spektrum receiver, which is also serial based, which is why I made this little deck that's hanging off the side here to carry it. And then on top of that is our IMU. I have been playing around with this design down here, tweaking things as I go along, but nothing too major. Let's take a look at this electronics deck. Here's the electronic stack carrier, and what I've got here is the battery harness here. So these basically are connected in series to take the 2 6-volt batteries into a 12-volt battery, and they're connected in series via the switch so you can power them on and off, so that breaks the circuit. The other thing I might do is replace this jumper. I think this is a power jumper there. I might replace this with a fuse and put like an 8 amp thermal resettable fuse on there. I quite like to fuse things which have large batteries in. Here's the electronic stack in place. Everything apart from the proto board that's supposed to be sat under here. I did fire this up the other day. This is the motor driver board. And they're designed to run off of a 3S LiPo, so that's about 11.1 volts, but they have a headroom of up to 12.6 volts. It does say that you're supposed to apply power to the board and then switch them on using this little switch. I was applying power from my PSU and switched on from the PSU, and this blew up. Now that was set at 12 volts. So I don't really see what the issue would be other than maybe a slight spike in voltage. It's not terribly encouraging, but the solution would be for me is to fit a DC-DC converter anyway, because I like to have a steady voltage. When these nickel metal hydrides come off charge, they'll be like 14 volts. That goes into the DC-DC converter, and that'll give me a steady 12 volts out. You'll notice during this series I won't be stopping to show you how to put together assemblies. And there will be a Facebook page available to go with this video series. Here's the new deck with the switch and the power distribution hub. I've added a inline fuse, so this is a resettable thermal fuse rated at about 5 amps continuous. I think the trip current's like 8 or 10 amps. The output of the switch harness goes into the input side of the DC-DC converter, and the output side of the DC-DC converter goes to the power distribution hub. I've reprinted this base with some of the changes that I've been making as I've been going along, and I've started to fill the lower chamber up with some lead shot. While I was putting this base back together, I decided to switch out the 3:1 ratio gearbox on the Lynmotion Servo to the 1:1 ratio. So here's 45 degrees in one direction, that's pretty good, and 45 degrees in the opposite direction. Yeah, and that feels about like the speed it should be. Once that big long lever's on the end of it, I think that's pretty much spot on. So it's really handy that I could just switch that 3:1 for a 1:1 gearbox. Let's take a look at what I've been doing with the CAD model, and in particular the head. So you can see at the moment it's pretty much fully assembled, and I've spent quite a lot of time on the neck and head part of the model. So let's just take a closer look at that. This is the base of the head. So I've added more bearings and changed a few other bits and pieces. This is now an aluminium tube, and I found some tube which is 14mm in diameter, and I think there's a 1.5mm wall thickness. So it's pretty lightweight, but strong, of course. I've changed quite a bit up here as well. Inside the main neck here, I've also gone again with my IGUS 8mm shaft. It's that nice hard anodized H8 IGUS axle. And then what I've got is I've got a bearing at each end. So there's a bearing here and there's a bearing here. I've got a shaft clamp on the end here, and that's just to stop this from coming back out. Most of that head box is the same. There's a few little alterations, but not much. It's mostly to do with this part here. At the end of the neck tube where these two parts joined, I have changed this part a little bit. It's just an 8mm hole for the axle to come into. I put an M3 nut in this space here, this cavity, which will have a grub screw going down just to hold on to that the axle there, hold it in position. I've put this M3 countersunk bolt in there, and the same arrangement will happen down the bottom here where it joins to the body. I'll show you what I do to drill these holes to get them in the right place. I make little jigs up for that, which I'll take a look at in a minute. A slot here for an M3 nut to go into. There's a bit of dressing that goes over that, so that will hide that hole. And then there's a 3mm hole here, which basically takes a very long grub screw. You self tap a grub screw into the end of this part here until it touches the end. So it kind of makes a bolt out of this part, if you like. This part is printed separately, and that holds a bearing. So then that whole arrangement just gets screwed in until it touches down onto that face. And that gives you a nice bearing surface for the push rod to work on. There's that axle clamp. So that just tightens up and grips the axle and holds it in place. The cables are going to come up through this hollow tube and then go down into this section here. You have this arrangement. So that's going to allow the cables to move in this slot, and they can just disappear out the end. They'll come out down here, and then obviously up into the neck area. Again, I'm sticking to serial protocol servos, and these are the smallest, lightest ones that I can find, and they are a Dynamixel servo. It's a 320-degree rotation, and they are super lightweight. So here's the yaw, and there's the roll. The yaw and the roll were mounted inside of this gator, and this is a solid part. I'm switching to make this into a soft material like Polyflex or Ninjaflex. It just means that this can be pushed out the way a little bit if need be, although to be honest that's probably more than enough movement. So with the head, I have separated the front nose cone. Again, that's partly me being lazy because it's a different colour, so it's easier for me to print and spray up afterwards. I obviously have to change the mounting inside of here because this is totally different. I've also left room on the plate for electronics. An Adafruit sound module here mounted underneath so that you can get to the screws from the bottom. The speaker is going to go in the front here, so it'll project sound out of the front of the cone. This is a new module from Lynmotion, which isn't actually out yet, but I should be getting one soon to try out. It takes serial data from the LSS bus, and it converts them to standard RC PWM outputs. I'll have the data coming up and probably going into this and then chaining on to these two Dynamixel servos, or I might have to run a separate bus for these. I'm not quite sure yet. So that's the plan with the head. It joins to the body pretty much the same way. There'll be a bolt through from the other side through this aluminium piece. You can see the two holes there. I've added more bearings down here in this part, so that's like a little M3 flange bearing. You shouldn't really run bearings onto a bolt because the bolts aren't made to go into bearings, they're the wrong size, but I'm sure it's good enough for this particular motion. Yeah, so that's pretty much it. Let's take a look at the actual model. Well, apologies for that fan noise in the background of that CAD segment, but my Mini 2 was running in the background, and although the printer's really quiet, the electronics fan is really noisy. Here's the model so far, and obviously the base we've already looked at, and now I'm onto this neck and the head area. So let's just look at this aluminium tube. This tube has been faced off on a lathe, so it's nice and square. What I do is just print a little block like that with a drill jig, a drill guide in it, and there's a stopper in the back there, so it'll only go so far on, so you know that the drill is going to be exactly the right place, exactly the right distance down the tube. I have another one on this end. Just push those on, sit them down flat on the surface so that the cubes line up, so that then both the holes are square with each other. So I drill from each side rather than drilling all the way through so the drill can't wander. After drilling, I deburr the inside of the tube with an 11.5mm drill bit and the outside with a countersink bit. If I were to put an M3 countersunk up here, it would go through an M3 hole in the tube, and then the back hole would have been tapped to N3 through a 2.5mm hole. Or you can just use a self tapper into the front hole on the tube. It's probably just going to be just as good, and if you don't have the taps, it's a lot easier. Here's the neck push rod. So I've got a bearing in the top here. This is a 10mm OD, actually it's a 6mm ID, I got that wrong in the CAD. And in the bottom here I've got a flanged bearing, 3mm ID, and I think it's 7mm OD and then an 8mm flange. This is the tiny pieces. Let's try that again. The bolt that holds the top of the push rod to the head. This just has a 3mm hole in it, which is kind of tight in the print, and I've just wound a grub screw down into that, so it makes a bolt out of this plastic piece. And then this is the back of it, this tiny piece here. Now this piece goes through the bearing like that. The bolt goes through there, and that gets screwed into the head box, which has that captive nut inside. Here's the neck axle. So not much to explain here. There's a captive nut down in there, and there's a grub screw down in the top, which is just biting onto that. That doesn't need to be hollow, it's just that I had a piece left over from when I was doing the body. The cables actually come out through there. Here's the neck box. So the cables go down through that slot and they come out at the bottom here, and of course there's a bearing there and a bearing in this end. The neck push rod joins through, and there's another captive nut in there for that grub screw to screw into. The roll and the yaw axis on the head, and this plate was actually all part of a gator in Michael's design, and this was all solid, and the servo mounts for the roll and the yaw were all joined inside of this solid piece of gator. This is all one piece. I've separated them out. I'm using these Dynamixel XL320 servos. They're pretty nice, they're lightweight, and they're serial bus. They use these little kind of plastic push rivets or pop rivets to hold them in place. I'm a bit snobby about using plastic rivets. Push down to the first section like that, and then you just push the cap in and it locks it in place. And you can't get them out unless you pull that cap out first. This gator will go over the top of here. This is printed in Polyflex, and what I've done to make it more flexible is I've actually only done one layer at the top. The bottom is a bit harder, it's 2 layers, and then this is 1 layer, so it's got quite soft. I might try NinjaFlex, and in fact I've got some here, as I know it's the wrong colour, but it is a little more flexible. So I might do it in NinjaFlex, black NinjaFlex instead. The point being is that it can sort of just deform a little bit if this roll servo needs to push it out the way. The head attaches to the servos in the same way using those pop rivets. So there's a plate up inside the head, and then there'll be some pop rivets to go in place on the top there. Place for electronics, the soundboard, and the new 2RC Lynmotion module there. And there's a speaker to go in the front of there, and this cone doesn't have the speaker hole yet because it was a previous model. That's about as far as I can go with this head mechanism right now. And one thing I should point out is that Michael was super careful to keep all of this really lightweight, and I have been adding a fair bit of weight to it. So there's no guarantee this is going to work yet. So what I need to do now is just get some movement out of this and see if I can get some stabilization going. Before I do that, I can't really tell how much further to go with this design. My replacement driver board has turned up for the MKR series. Firstly, I did have to upgrade the firmware on it. It was running quite an old version of firmware, and there's a firmware updater included in the example sketches. There's 2 motor drivers on board, Motor 1 and motor 2 are the lower end 3 amp driver, and motor 3 and 4 are the higher end 5 amp drivers. Processor also runs the servo outputs directly, so that also takes load off of your Arduino. Anyway, I've got something working just to show you the difference between the closed loop and the open loop mode. I had to remove my DC-DC converter because it wasn't going to do the job, because it turns out it's a step-up converter. And what I want is a more like an isolated DC-DC converter where it takes anywhere between 9 and 30 volts in and gives you 12 volts out. Still got my nickel metal hydrides in there, but I'm just being very careful to make sure that they're not freshly charged, because they come off charged at about 14 volts. And I've got a couple of diodes in series with them as well, so it drops the voltage by another 1.2 volts, because I'm slightly worried about that 12.6 volt maximum input voltage to the maker motor shield. What I've got at the moment is this motor here is running in open loop mode. In fact, it's running at about the slowest possible duty cycle where it will actually move, but as you can see it's stalled at the moment. There you go, now it's started. And obviously it's quite easy to stall, there's not much power there. But this one here is the closed loop version. I'm able to get this one running much slower. I'm actually closing the loop on the revolutions per minute. So I've set the RPM on this at about 35, and it's monitoring the encoder and matching that RPM. Anything slower than this, it does start to struggle a bit, but you can see how much slower it is than the open loop version. See, this one I can stall quite easily. This one, if I try to stall it, it will ramp the power up, so it's going to try and keep that constant speed. With a system like Dio, where you've got a wheel driving on each side, if one of the wheels gets stalled on something, it should then up its power and try and keep Dio in a straight line. Well, I'm nearing the end of this video, but before I wrap it up, I'm going to try and get some movement out of Dio. I'm going to reassemble the wheel, then I can really give those motors a good test. I've also reprinted the tyre, and here it is in white. This is a Polyflex by Polymaker. One of the problems I saw on the black tyre was that there's a seam down that edge there. I think you can just about see it, like a scar. And it's where the extrusion starts and stops each time. It starts in the same place and leaves this scar on the tyre, which leaves a hard spot in the tyre. And as it was rotating round, you get a little dunk-dunk as it went over the hard spot. I've reprinted it with random start points, and basically that's got rid of the seam. So hopefully that's going to be better. One nice feature about having Wi-Fi on the Arduino that I'm using is that right now Dio is set out in the hallway there, and I can upload code from the Arduino IDE using the over-the-air library. Dio is actually his own Wi-Fi access point, so currently the PC is a client on Dio's server, so I can upload a sketch remotely. There you go, it's uploaded now. Dio debug client, and I can get back debug messages over Telnet. So I've got the kill switch here, so I can just turn him on with that, and right now I've just got forwards and turn controls on the stick here, and there's a little bit of IMU being used to balance the body, but quite basic. This is literally my first attempt, and of course there's no tyre on it at the moment, so once I put that tyre on, I'm pretty sure it's not going to want to turn on the spot because this carpet is quite deep. Quite happy with the speed though. Well, it's really not very happy with that tyre in place. I've obviously got too much of the tyre touching the floor, because turning on the spot now is much harder. It's achievable, but there's not much grip left at all. Right, what have I got to sort out? Well, currently the batteries are just about impossible to get in and out without you take the wheel off, but the wheel does come off rather easily, so I'm not too worried about that. The electronics are pretty good. The over-the-air link is working really nicely, which makes it really easy to do firmware updates. The wheel is obviously too tall here, it's causing too much friction. I might just make the green rims bigger to try it and see if that works, and see how much bigger I need to make it, so I can figure out how much smaller the tyre needs to be. I think the thing that's going to improve it a huge amount is getting those closed loop feedback motors in there, which will at least allow me to govern the speed properly of each rim. You'll find the usual information and links to parts that I'm using in the description section below. And there's also a Facebook page now to go along with these videos that Lee Towsey's kindly set up for me. I'll also leave a link to that in the description below. Bye! All of that in the shop.